So recall that last time I defined the notion of group and subgroups, and I also stated some examples of both of them. So suppose now you have a group which is a non-trivial. That means it has more than one element, and you start off with a uh, non-identity element. By the way, so from now I will define just star. I will replace it by dot. So, and also I will write say a star a star a. Say there are n many of them, so I will just write a to the power n. So don't get confused with the usual multiplication notation. This is just for the sake of convention. I'm just writing it as a power n. This is not the usual multiplication. It depends on the operation that we are talking on a specific group. So yeah. So now suppose we have a non-trivial element in the group, and so remember the definition of the group says that if you pick two elements from the group, their binary operation, like if you do this a star b, that must also be inside the group. So if you pick a and you operate a with itself, then you get a square. So then a square will also be inside the group G by definition. Similarly, if you pick a square and a, you will get a cube. That is also in G. And so all powers of A must be in G, right? So in fact we get that. So let's collect all elements of this form. So yeah, right. So this is clearly a subset of G. And moreover, if you take if you take two elements of the set H, so any element would look like A power n for some n, right? So let's pick two elements, A power n and A power n prime. So these are two elements from the subset H. And so suppose now if you see that if you do the binary operation, then you get a power n plus n prime. But that is again in H, right? And if you pick any element a power n for a power n in H, we already have their inverse, precisely a power minus n, right? Because when you operate it with a power n, you will get just a power 0, which is just the identity element. And so similar thing will hold for this. So moreover, this becomes a subgroup, right? Because it in this subset we already have the closure property that whenever you pick two elements from the subset, you get their product to be inside that, and also for each element you have an inverse. And of course, if you pick n to be 0, you get identity element. Yeah, and associativity holds from the definition of the group because this is just a smaller collection of elements from the original group. So this becomes a subgroup. And because any element of this subgroup comes from a single element, right? You started off with a single element and you operate it n many times, you get this a power n for each n. So because it comes because every element eventually comes from say a single element, we call this group uh, a cyclic group, and we call this element E to be its generator because every element is generated by E. So moreover, this is said to be the cyclic group generated by A. A is the generator of this. So we get a subgroup that is generated by a single element. And moreover, so it may be the case that H is a whole of G, right? So if this happens, that H is like entire group G. So if this happens, then we call it G is a cyclic group with generator A, generated by the element A, and we write it as this. So we get a cyclic group. Now, the first basic example is Z plus because here every element is generated by 1 because if you pick any integer, uh, you would get like say n is any positive integer. So you can write it as right n many times. So every element comes from the element 1. This is cyclic group with generator 1. Now, say for example, now the question is whether this is cyclic. So is this or this is cyclic? These are natural questions. Yeah. So maybe you can think about these things. These are some of the questions that you can think. Another example, last time I defined these finite groups. This is again if you pick any element. Remember, every element represents an equivalence class in this group. So any element would precisely be representative of this class. So let me just define. Let me just take it as k bar. That is generated by again if you write 1 bar k many times, right? Because that is how we define the group operation. So again, this is uh, say generated by 1 bar. So this is a finite cyclic group, and of course Z is an infinite cyclic group. Yeah. So we get that for every integer in, we always have a cyclic group of that order by example B. Well, so yeah, so you talked about generating element and uh, cyclic and what is a cyclic group? So yeah, so now let us come to some more properties of subgroups. So far we have not seen any particular example of a subgroup. So basically, this thing is a bit abstract, right? Because we have not like we're not talking about a particular group. We're just taking an abstract group of order at least two, and we're claiming that uh, this is one sort of a subgroup inside that. But precisely, we have not talked about any particular example, right? But if you observe that, we always have a particular subgroup. Precisely, if you take any non-trivial element and you take the cyclic group generated by that element, it may be the entire group G, but anyway, it will always be a subgroup of the group. So, for example, uh, let me just call it A prime because we're taking the same group Z. So, you can take, say, any element which is non-trivial, say, for example, 2, and you can talk about the subgroup which is generated by 2. So, this means all multiples of 2, all even integers. So, yeah, this is a subgroup. And this is a proper subgroup because this is strictly smaller than Z. Also, we can talk about any element in, right? So these are precisely multiples of n. If n is 1, you get the entire group Z, otherwise you get something smaller. Yeah. So we always have subgroups inside a group. Like there are cyclic subgroups. So yeah. So let us now come to what is coset of a subgroup. Coset and the first fundamental theorem in group theory, the a relation between order of a group and a subgroup. So by order, I mean the cardinality of elements. So basically, we are always talking about finite group because otherwise order won't make sense. So this is noted by order of group G, and we always take H to be the subgroup of order of the subgroup to be mod H. Or sometimes you can some books refer to as O of H or O of G anyway. So yeah. So let's see what is the relation between this. And throughout this discussion, I will take the group to be a finite group. And so H will automatically be finite because it is smaller than the order of the group. So yeah. Now, so let's see what is a coset. So if you pick any element from a group G. Select. And to avoid triviality, I will always pick non-identity elements. So for me, this order is at least two. The subgroup order must be, it can be one, but the order of the group is at least two. Otherwise, everything becomes pretty trivial. So you take a non-identity element and you have a subgroup. So we define this by this notation to be. So you take an element of the group A and you multiply each element of each from the left. You can do it. This operation is basically the operation of the group, and this is elements of subgroup. And we are multiplying the element A from the left. This is called left coset. Similar things you can do it from right, so that will be called what is a right coset. So this is left coset of A. Yeah, and you can do this thing for every element, right? Like for every element of G, you can talk about this A capital H, things like this. Yeah, and so what you can do, you can now take a relation like you. I'm defining. So let's see. It will all make sense after some time. Uh, like why I'm doing these things. So I'm defining a relation on G that you have two elements from the group A and B. They are related if and only if B is AH for some H. So what does it mean? It means that this means that B is inside that coset. So basically, we are taking this left coset of A, and this will be again a bunch of elements from the group G. And if your chosen element B belongs to that set, you say B and A are related. And so the easy thing would be to verify that it is an equivalence relation. I'm not verifying it. And so what equivalence relation does? Partitions a set. And here the underlying set is the group G itself. So you can take, so G will be a disjoint union because it's partitioning of H. A belongs to G, right? And or maybe I should not G, maybe some. So basically, we are taking each equivalence class and we are choosing a representative. So let's call the collection of representatives or collection of distinct representatives because we are taking distinct elements. Otherwise, it doesn't make sense. Let's call the set to be X here. So we get G is disjoint union of this age, but each age has same number of elements because everything what we are doing is just multiplying a particular element from the left. So each age will have order or cardinality. Remember, we're only talking about finite things, right? So every set is finite. So from here you get that order of G. This will be just union of age or sum of the cardinality of age, and each age is just this, right? Because if you pick any element from each and you just take this becomes a bijection, right? Because precisely for any element H you have A inverse H here. So yeah, so this becomes a bijection. So these two have same number of elements. So you get order of H times order of X. So what does it imply? It implies that this is the order of the subgroup, and this divides the order of the group. So this is precisely a Lagrange's theorem. So given any finite group, any subgroup has must have order that divides the order of the group. So yeah, and this so now it makes sense to talk about this ratio, right? Because this becomes a natural number, a positive integer. This is called index of the subgroup. index of the subgroup inside the group G, and we denote it by sometimes in this fashion or index of the subgroup H in G. Yeah. Basically, this order is same as the order of X. And similar things you can do it by taking the right coset business, but that is again same. Yeah. So we get that any finite group has subgroups that have order must be a divisor of the original group, order of the original group. So yeah. So the first thing to notice here is if the order of the group is a prime number. So if this is a prime number, that means the only divisors are 1 and p itself. So the possibility of any subgroup is that either it has order 1 or it has order p. So if it has order 1, it must be trivial, and if it has order p, that means that this is same as, so these two have same number of elements, and because this is a subgroup, this is a subset, so it forces the subgroup to be the entire group. So any finite group of order prime number cannot have any proper proper non-trivial subgroup. So this is the first small observation. Yeah. Now, so this is what Lagrange's theorem. So the next question, the most natural question is whether the converse holds or not. Converse means that given any group G and any divisor of its, so we're talking about finite groups again. So given any group G and a divisor of that group, whether there exists a subgroup of that order. So if order of G is n and K divides n, whether there exists a subgroup, we denote the subgroup by this notation, H of G, such that order of H is K. So there is a converse question. We will come to it later. There is a natural thing to think about. Yeah. So so far we have seen that the order of the group and behaves a nice way, and we have also seen what is a cyclic group. So now we can talk about order of an element. So what does it mean when you talk about order of an element? So suppose that, say for example, this z mod n z, you start with the element 1 and you add it twice, you get 2. You add it thrice, you get 3. If you add it n many times, you get n bar, right? By the definition, because this is same as n times. So yeah. But what is this? This is just same as the class of 0, right? Because remember the way we have defined. A bar and B bar are same if n divides A minus B. So here n divides n minus 0. So these two are same. So we get the identity element back by adding the generator n many times. So in general, if uh, say if A is a non-trivial element in a group G, then by order of G or order of A in G, we talk about minimum of all those elements, all those natural numbers in, such that when you operate n times the element A, you get identity, right? So minimum of all such natural numbers, you define it to be the order. For example, here, if you add n times, you will get 0. So if you add 2n times, you will again get 0. But n is the smallest one, right? So here the order of 1 is precisely n. So that is the definition of what is an order of a particular element. So yeah. Next time, I will talk about more on cosets, uh, subgroups of cyclic groups. So here we have seen subgroups of any group. So particularly, we'll see subgroups of cyclic groups and order of element. So we'll talk about these things next video.